Ask most scientists today, what are protons made of? They will likely respond protons are made of quarks. And although no free quark has ever been observed in nature, people have claimed quarks exist inside protons for more than 50 years. The problem is that the experimental results from examining the internal structure of the proton do not support this claim. In fact, they suggest the building blocks of the proton are likely some variation of muons, particles that are routinely seen in the subatomic realm. Why is this not known? Continue watching to find out what protons are really made of. In the early 1960s, most particle physicists believed protons were homogeneous particles, having no internal structure. During that time, Murray Gell-Mann showed how baryons, including the proton, exhibited periodic behavior in a scheme he called the eightfold way. He found that if the baryons are made of particles having fractional one-third charges he called up, down, and strange quarks, he could explain this periodic behavior. From that, Gell-Mann claimed protons are made of 2 up quarks and 1 down quark. Nonetheless, most particle physicists considered his quarks to be theoretical entities that did not really exist.
But quarks were only considered as one convenient way to model SU3 symmetry. Quarks were not considered real particles.
They still thought the proton was homogeneous. In 1967, the Stanford Linear Accelerator Center, SLAC, along with particle physicists from the Massachusetts Institute of Technology, MIT, began conducting experiments called deep inelastic scattering, aimed at determining if protons are homogeneous. These experiments fired high-energy electrons into protons, expecting them to pass through the protons, essentially undeflected. Instead, the electrons shattered the protons, scattering at various angles, indicating they were hitting things inside the protons. SLAC determined that those things were charged particles. Finding particles inside the proton caused the once skeptical physicists to believe that Gell-Mann's quarks were real particles and that his proton model was valid. The electron scattering data was compiled into proton structure function values called F2. The F2 values were plotted as a function of the fraction of the proton's momentum, x, the probing electron producing the F2 value encountered when it scattered. Particle physicists determined that the F2 curve should go to 0 as x approached 0, causing it to peak at the x that is the reciprocal of the number of particles forming the proton. This indicated the fraction of the proton's mass each particle forming the proton carried. Since Gell-Mann claimed the proton is made of 3 quarks, this meant that its F2 curve should peak at momentum fraction x equals 1/3 to validate his model. When the proton F2 data was plotted, the curve did not go to 0 as x approached 0, nor did it peak at x equals 1/3. Points clustered about the value F2 equals 0.35 from near x equals 0 out to x equals 1/5. This was interpreted as the curve staying flat from x equals 0 to x equals 1/5. Then the F2 values gradually fell towards 0 as x approached 1. All of this appeared to invalidate Gell-Mann's 3-quark proton model. Expecting to validate Gell-Mann's model, the SLAC MIT team was puzzled by this result. At this point, it had 2 options: acknowledge that the experimental results falsified Gell-Mann's model and begin building a model that fit the results, or ignore the true implications of the results and devise a way to make the results fit the model. The team chose the latter. They declared that in addition to the 3 real quarks Gell-Mann proposed, dubbed valence quarks, the proton also contained a large number of virtual quark-antiquark pairs, eventually called C-quarks. The valence quarks are the substance of the proton, while the C quarks, which are virtual up, down, and strange quark-antiquark pairs that pop in and out of existence via pair production and annihilation from latent energy within the proton, are fillers. Finally, they claim that chargeless, force-carrying particles called gluons are also needed in the proton to bind the quarks together and allegedly carry about 1/3 of the proton's mass the scattering electrons could not see. This is the proton model currently in place. 2 up quarks and 1 down quark, a sea of virtual quark-antiquark pairs, all held together by a collection of gluons. Several electron-proton deep inelastic scattering experiments were done after the SLAC experiments from the end of the 1960s. Facilities like the Hadron Electron Ring Accelerator, HERA, produced results that were interpreted to validate the original SLAC results in the prevailing proton model by showing F2 does not go to 0 as X goes to 0. However, the results of a set of experiments done at the Thomas Jefferson National Accelerator Facility, JLab, appear to tell a different story. Performed around the year 2000, the results of the JLab experiments were not published until 2010. When combined with the original SLAC results, they show that the proton F2 curve is not flat from x equals 0 to x equals 1/5, but goes to 0 as x approaches 0, producing an F2 peak at x equals 1/9. This peak indicates that the proton is made of 9 particles, not 3 as Gell-Mann's model requires. The significance of this result is that all of the JLab momentum transfers, q-squareds, are comparable to the SLAC q-squareds, while the HERA q-squareds are up to 3 orders of magnitude higher than SLAC. The probing electron wavelength in Fermi, 10 to the minus 15 meters, is roughly 1 over the square root of q-squared. For x between 0 and 0.2, SLAC q-squareds range from 0.56 to 4.00 GeV squared, making its electron wavelength between 0.50 Fermi and 1.32 Fermi. By comparison, JLab q-squareds range from 0.034 to 1.365 GeV squared, resulting in electron wavelengths between 0.855 and 3.95 Fermi, comparable to SLAC. However, the HERA q-squareds range from 4.5 to 1,600 GeV squared, producing electrons with wavelengths between 0.025 and 0.47 Fermi, 20 to 34 times shorter than SLAC. This means the HERA electrons see finer detail within the proton than SLAC or JLab electrons. Consequently, the JLab results are extensions of the SLAC results, while the HERA results are mostly incompatible with the SLAC results. Again, here is a result that appears to invalidate Gell-Mann's 3-quark proton model. However, the 3-quark model lives on because this combination appears to have never been analyzed. With a mass equal to 1,836 free electron masses, a proton made of 9 particles gives each of its component particles a mass of about 204 electron masses. This makes the muon, with a free mass of 207 electron masses, a strong candidate for the proton components, considering muons bound inside a proton would be slightly less massive than free muons. Since the proton carries a unit positive charge, being made of 9 particles, it appears protons are likely made of 5 positive muons and 4 negative muons. No fractional charges needed. In electron-proton deep inelastic scattering, an F2 curve with a blunt peak much less than 1 indicates the particles inside the proton interact strongly with each other. The particles cluster together like protons and neutrons do in the nucleus of an atom. The blunt SLAC JLab proton F2 curve, peaking at about F2 equals 0.35, shows that the 9 muons making up the proton are clustered together. A tightly packed symmetrical cluster of 9 spheres, contained within a larger container sphere, would require each smaller sphere to have a radius of about 0.366 times the radius of the container sphere. The charge radius of the proton is about 0.84 times 10 to the minus 15 meters. So a proton containing 9 muons within this radius would make the radius of each muon about 0.31 times 10 to the minus 15 meters. Now, deep inelastic scattering appears to show the proton is simply 9 muons, 5 positive and 4 negative, each having a mass of about 204 electron masses and a radius of about 0.3 times 10 to the minus 15 meters, tightly clustered together within the proton radius of 0.84 times 10 to the minus 15 meters. Unlike quarks, which allegedly carry fractional charges and have never been seen individually, muons are particles with unit charges that are routinely observed as collision fragments and decay products of other subatomic particles. All things considered, deep inelastic scattering clearly favors real muons as proton components over imaginary quarks. It is time to put this flawed model of the proton behind us. In the next video, deep inelastic scattering peers even deeper into the structure of the proton, revealing that its component muons are not fundamental particles, as the standard model claims, and why, once again, particle physics has failed.